Hello, my name is Ilya Levitsky. I'm a researcher from Wireless Networks Lab in Institute for Information Transmission Problems. In this video, I'm going to demonstrate you a NOMA Wi-Fi prototype that uses a new feature, Constellation Rotation functionality. NOMA stands for Non-Orthogonal Multiple Access, a technique that allows a transmitter to send multiple streams to different users using the same time-frequency resources. You may remember our first video with NOMA demonstration. Well, in this video, we are going to dive into the problems that NOMA transmissions face and our solution for this problem. Here I have an USRP running an 802.11 application framework with some modifications so that the framework supports NOMA. Now I'm going to start a transmission from one antenna to the other. Here we go. Now you can see a real Wi-Fi transmission. You can notice that the signal quality degrades if I put a hand between the antennas. This is a regular Wi-Fi transmission, and I can switch between different modulation types for it. For example, here we can see a 16 QAM constellation. Now we can switch to QPSK modulation or BPSK modulation. Now let us turn on NOMA. Like this. Now you see that apart from the same BPSK signal, we add another 16 QAM signal of lower power. We call this 16 QAM low power signal secondary signal and the BPSK signal primary signal. The secondary signal can be destined to a nearby station that can resolve these little details. And the primary signal can be destined to a further station, which can resolve only large-scale details. Let me demonstrate that a laptop can indeed receive primary frames. Now I have Wireshark turned on this laptop, a program which tracks incoming frames from, in this case, wireless channel the USRP operates in. Primary frames are destined to the laptop. Its MAC address is set as the destination address of the primary frames. So the laptop successfully decodes them. We can even change modulation encoding scheme of the primary frame dynamically. Now we make USRP to receive both signals, so we can see the throughput for each of them. Let us pay attention to the secondary signal. You may notice that the constellation is smeared along a vertical axis. Also, can you see that one side of constellation is distorted more than the other? Well, that is phase noise, and this type of noise is very common for wireless transmission of QAM modulated signal. Phase noise becomes a real problem for NOMA, since its effect is proportional to the amplitude of the symbol. The greater is the symbol, the bigger is the distortion. Small constellations with fine details suffer a lot from phase noise, because it causes a noticeable distortion along a certain axis. But we can minimize the negative effect of phase noise by rotating the direction by 45 degrees. And we can do it by simply rotating the small constellation itself. Like this. Now the phase is acting along a different direction, so that there is no that much interference between the symbols. Maybe it is hard to notice, so let us look at the throughput for the secondary signal. You see that throughput drops when I change the rotation back to default, down to 7.5 megabits per second. And it goes up to more than 8 megabits per second when I rotate it by 45 degrees. But what happens when I change the primary constellation to QPSK? Now the direction of phase noise changes, so for better secondary signal reception, we should rotate the constellation back. This means that the performance of NOMA depends not only on constellations of primary and secondary signals independently, but on their combination. Choosing the constellation of one signal has an effect on the other one.
During our research, we have conducted a series of experiments to find out a portion of undamaged secondary frames that reach the receiver. We have built a dependency of frame-receive ratio on signal-to-noise ratio for the secondary signal. We vary the SNR by changing the alpha parameter, which is the power fraction of the secondary signal. Alpha can span from 0 to 0.5, and the SNR changes accordingly. So the curves here indicate the frame-receive ratio versus SNR dependency, and their parameters are modulation for primary and secondary signals, as well as the angle of rotation, 0 or 45 degrees. The red color represents BPSK for secondary signal. Line types indicate the primary signal modulation, and point types indicate the angle. You can see that for the best performance, secondary constellation should be rotated if superposed with primary QPSK, and should not be rotated with primary BPSK. In these cases, the phase noise acts in a perpendicular direction to the secondary BPSK, and hence has no effect on the reception. If we change the rotation, the situation only worsens. The difference here is 3.9 decibels of SNR, so rotation can really influence the reception. There is also a difference of behavior for secondary QPSK and 16 QAM. Rotate when primary is BPSK and don't otherwise. The performance difference of secondary 16 QAM superposed with primary BPSK has already been shown in the demo. The superposition with primary 16 QAM shows a good performance, but the exact reasons for that is our future research. Finally, on the right part of the graph, lines start to drop. And this is explained by the fact that secondary constellations are too big and start to overlap. This causes unwanted errors when decoding, so we better avoid using such big values for alpha.
So a simple constellation rotation can upgrade secondary signal quality for better NOMA performance. I hope that this demonstration is a good evidence that constellation rotation is an important amendment to NOMA concept. Thank you for watching.